So welcome back, my dear students. Today's class we are going to see a numerical problem on how to design a beam if it is subjected to a bending moment, a shear force and a torsional moment. So the question is, design a beam 600 mm by 800 mm overall depth subjected to a given bending moment 260 kN meter, shear force 180 kN and a torsional moment 300 kN meter. Use M35 grade concrete and Fe 500 grade steel. So here the additional torsional moment is coming, and these are the working moments and shear force is acting on the beam. So we need to go for design values. That is, design values I could write the given values are B is equal to 600 mm, total depth is given as 800 mm. I will assume an effective cover of 50 mm. And I will get the effective depth as 800 minus 50, that is 750 mm. Now the factored or the ultimate shear force, bending moment and torsional moment, I could write it as, here is dead load and live load, so I could take it as factored or design value for your bending moment and shear force, that is ultimate or factored bending moment is equal to factor safety into 1.5 into 260, that is 260 plus 130, you get it as 398 kilonewton meter. Similarly, ultimate or factored shear force is equal to 1.5 into 180, that is 180 plus 90, 270 kilonewton meter, and factored torsional moment I'll get it as 1.5 into 300, that is 450 kilonewton meter. So we need to design it for these three values. So the first one is, we will design it for the combination of bending moment and torsional moment, and the second one is we will design it for transverse reinforcement, that is the combination of shear force and torsional moment. So if we take clause number 41.4, the reinforcement member subjected to torsion, we have seen in the last class. Here the reinforcement for torsion when required shall consist of longitudinal and transverse reinforcement. So the first design is longitudinal reinforcement, that is clause number 41.4.2. The longitudinal reinforcement shall be designed to resist an equivalent bending moment ME1 given by ME1 is equal to MU plus M1, where MU is the factored bending moment, M1 is equal to TU, that is a factored torsional moment, into 1 plus D by B divided by 1.7. So we will substitute these values and we will get the value for M1, and from there you will get the value for your equivalent bending moment ME1. There is a design for longitudinal reinforcement. The reinforcement member subjected to torsion shall consist of both longitudinal and torsional reinforcement given in 41.4.1, where we need to find the value for your equivalent moment, where equivalent moment ME1 is equal to MU plus M1, where MU is the factored bending moment. You value, we got it as 390 kilonewton. So M1 the God has given the value as M1 is equal to TU into 1 plus D by B divided by 1.7, where TU is the factored or ultimate torsional moment. So this value is your TU, this value is your MU, and this value is your VU. So from here, substituting the value for this, you'll get it as 450 into 1 plus D. The total depth of the beam is given as 800 mm. We will substitute in terms of meter, that is 0.8 by the width of the beam is given as 600 mm, 0.6 the whole divided by 1.7. You will get this value as 617.647 kilonewton meter. So this is the value for M1. Now from here you'll get the value for ME1 as MU plus M1, that is MU value you have it as 390 kilonewton meter, that is 390 plus 617.647. You will get this value as 1007.6, nearly 1008 kilonewton meter. Now this has to be designed as flexural reinforcement in the tension phase. Now the clause number 41.4.2.1 says, clause number 41.4.2.1, you can say if M1 is greater than MU, if M1 is greater than MU, then we need to design it for another moment, that is ME2. Here you can see M1 value is 617.647, which is very much greater than your MU. That is here 617.647 is greater than MU, that is 390 kilonewton meter. This is also kilonewton meter. So I could say I need to design it for a value for ME2, where ME2 is given as ME2 is equal to M1 minus MU, that is 617.647 minus 390. I'll get this value as 227.647. Nearly I'll take it as 228 kilonewton meter. So this ME1 has to be provided as tension reinforcement or as flexural reinforcement in the tension phase. Flexural reinforcement in tension phase, and this ME2 has to be provided as flexural reinforcement in compression phase. That is what the code says in clause number 41.4.2. Now if you read the clause number 41.4.2.1, you could see if the numerical value for M1, that we got it as 617.647 as defined in 41.4.2 exceeds the numerical value of the moment MU, that is your 390, longitudinal reinforcement shall be provided on the flexural compression phase such that the beam can also withstand an equivalent ME2 given by M1 minus MU, the moment ME2 being taken as acting in the opposite sense to the moment MU, that is it should be provided in the compression phase. So now we'll design for ME1 and ME2. There is design of longitudinal reinforcement for ME1 moment. I need to check whether this section is an under reinforced or over reinforced section. So I'll take the MU limit value, that is Q FCK BD square. We have Q for FE500 as 0.133 and the given FCK is FCK 35, that is M35, you'll get it as 35 into B is 600 into D is 750 square. You will get this value as 1571.06 kilonewton meter. That is ME1 is less than MU limit. You can take in terms of D minimum also. Also the same thing will happen. So I can say here is an under reinforced section. Is an under reinforced section. So the value for ME1 I could write it as ME1 is equal to 0.87 FYAST into D minus 0.42 XU. That is ME1 is equal to 0.87 FYAST into D minus 0.42 XU. You have ME1 value as 1008 kilonewton meter, FYS 500, D as 750 and XU, that is you can equate tension and compression, you get XU as 0.87 FYAST divided by 0.36 FCKB. You will get the value for this AST by solving the quadratic equation. So solving this equation, you will get the value for AST. That is, you will get a quadratic equation. There are two roots. You will get the value for AST as 27 554.63 mm square, or AST is equal to 3479.844 mm square. So we will take the smaller value for AST. Now we need to check for AST maximum and AST minimum. You will get, as in case of beam, AST maximum is 4% of PD, that you will get it as 19200 mm square, and AST minimum is equal to 0.85 BD divided by FY, you will get it as 765 mm square, which means the AST provided, AST required is fine, 3479.844 mm square. So we will provide 6 numbers 28 mm bar, 6 numbers 28 mm bar. So that area AST provided will come as 3694.51 mm square. So we will provide for a moment of ME1 3694.51 mm square, that is 6 numbers 28 mm 5 bar at the tension phase. Now the design of the longitudinal reinforcement for ME2 moment. This is provided in the compression phase. You could see in clause number 41.4.2.1. It is written for longitudinal reinforcement for ME2 moment. This is provided in the compression phase given in 41.4.2.1. I could write ME2 is equal to the stress into tensile force into lever arm, that is 0.87 Fy. I'll call this corresponding AST as AST2 into, I could write the lever arm will be D minus D dash. That is, I can write 228 into 10 raised to 6 is equal to 0.87 into 500 into AST2 into D 750. I will assume the D dash value as also, that is the compression phase cover was also 50 mm. So this I will get the value for AST2 as 748.76 mm square. So I will provide, this is AST2 required, I will provide 4 numbers 16 mm 5 at the compression phase, 804.24 mm square, and this will be provided at the compression phase. So now the longitudinal reinforcement is done. We will see the case of side-face reinforcement at the end. Now we need to design it for the transverse reinforcement given in clause number 41.4.3. So if you see clause number 41.3 and 41.4.3, you could see the design procedures for the shear reinforcement or transverse reinforcement. When there is shear and torsion, there is an equivalent shear that is given by VE, and VE shall be calculated from the formula VE is equal to VU plus 1.6 TU by B. So this equivalent shear force, equation for equivalent shear force and equation for equivalent moment you need to by heart, because this can be asked for your competitive exams. So you need to by heart these equations, as well as sometimes there can be numericals asked, or sometimes direct equation can be asked. So this VE is equal to VU plus 1.6 TU by B, where VE is the equivalent shear. The equivalent nominal shear stress tau VE, that is VE by BD, that is the equivalent nominal shear stress. In this case shall be calculated as given in 40.1, except for substituting VU by VE. The values of tau VE shall not exceed the value for tau C max given in table number 20. And it is similar to your shear case. If the equivalent nominal shear stress tau VE does not exceed your tau C, that is the shear given by your main reinforcement and concrete given in table number 19, then the minimum shear reinforcement shall be provided. This is the same case as that you have discussed in case of shear. That is, when tau VE is less than tau C max, tau C, then there is no need of providing shear reinforcement. We need to provide minimum shear reinforcement, and in no case tau VE value should be greater than tau C max, that is the maximum shear capacity of a section. You have the equivalent shear force VE given by the equation VE is equal to VU plus 1.6 into TU by B, that is substituting that value. VU is 270 plus 1.6 into TU is 450 divided by B is 0.6. You will get this value as 1470 kilonewton. Now equivalent nominal shear stress value, that is tau VE. Tau VE, I can write it as tau VE is equal to VE by BD. I'll get this value as 3.26 Newton per mm square. Now if you see table number 20, tau C max for M35, you will get from table 20 M35 grade concrete, you will get tau C max value as 3.7 Newton per mm square, which means tau VE is less than tau C max, hence safe. Now we need to get the value for tau VE, that is your, now we need to get the value for your tau C, that is the shear taken by your concrete and main reinforcement. So in order to get the value for tau C, that is, you need to get 100 AS by BD from table number 19. You need to calculate the value for 100 AS by BD, that is 100 into AS is pi by 4 into 6 into 28 square divided by 600 into 750. You will get this value as 0.821. So from table number 19 of your IS 456 corresponding to your M35 grade concrete, you need to get the value for tau C. You have for, from your table number 19, you will see you have for 0.75, you have the tau C value as 0.59, and for 1 you have the tau C value as 0.67. So by doing linear interpolation, you will get the value for 0.82 as you, after linear interpolation, you will get the value for tau C as 0.612. This you will get as 0.612. So that is tau C value you will get as 0.612 Newton per mm square by linear interpolation from table number 19. So which means here your tau VE is greater than tau C. So which means you need to provide shear reinforcement. So provide shear reinforcement. So you can see here the only change is we have changed it by tau VE instead of tau V. So you can see designed for shear reinforcement in 41.4.3, provide 2-leg 10 mm stirrup of FE 415 grade. You are providing a smaller grade steel because this will be more ductile when cut, and it will be very easy for you to bend the bars. So if we go to 41.4.3, you can see 2-leg closed stirrups enclosing the corner longitudinal bars shall have an area of cross section ASV given by ASV is equal to TU SV divided by B1 D1 into 0.87 Fy plus VU SV divided by 2.5 D1 into 0.87 Fy. So if I take the SV common here, I will get the equation as SV is equal to 0.87 Fy ASV into D1 divided by TU by V1 plus VU by 2.5. That is rearranging, I'll get the value for SV. From there, you'll get the value for the spacing required. Before that, you need to understand what is B1 and D1, which I will explain in the coming minutes. Okay, so rearranging and writing, I'll get SV is equal to 0.87 Fy ASV D1 divided by Tu by B1 plus Vu by 2.5. Now we need to get the value for this B1 and D1. B1 is the center to center distance between the corner bars in the direction of the width, and D1 is the center to center distance between the corner bars. That is, if I am plotting the reinforcement detailing of this, I'll get it in this way. That is, so we have designed up to here, that is, we are providing 6 numbers of 28 mm diameter bar at the compression tension phase and 4 numbers of 16 mm bar at the tension phase, and I am assuming 2-legged 10 mm stirrup of Fe415 grade steel. Now B1 is the shortest distance between the reinforcement corner reinforcement along the length. So if I am taking, I'll get this distance as B1, that is from center of this reinforcement to center of this reinforcement, this distance is B1. So if I am assuming this cover as side cover as 50 mm, side cover as 50 mm, I will get B1 as B1 is equal to 600 minus 50 minus 50, that is 500 mm. Similarly, D1 is the distance between the corner reinforcement along the length. That is, I will get D1 from here, from center to this distance, this is D1. So if I am taking the cover, I have already took the cover, this is 50 mm and this is 50 mm. So I'll get D1 as 800 minus, I'll get this D1 as 800 minus 50 minus 50, that is 700 mm. Substituting that value over here, you will get value of SV as SV is equal to 0.87 into 415 into 2 into pi by 4 into 10 square into 700 divided by Tu. Tu value you have it as 450 Newton, kilonewton meter, 450 into 10 raised to 6 divided by B1 is 500 plus Vu we have the value as 270, that is 270 into 10 raised to 3 divided by 2.5. You will get this value as 39.38 mm. You will get this value as 39.38 mm. The spacing is very small. To ensure the spacing or to increase the spacing, increase the diameter of the stirrup. That is, this is very small, so we will increase the diameter of the stirrup such that the spacing will increase. So here only the difference is this 10 square. So I will divide it by 10 square and multiply it by another diameter, that is I will assume 12 mm diameter bars. That is, the only change here is the 10 square. So I'll divide it by 10 square and multiply it by 12 square. So to increase the spacing, we will increase the diameter of the bar. Assume 12 mm, assume 2-legged 12 mm 5. So you'll get the new spacing as SV is equal to 39.38 divided by 10 square into 12 square. You will get this value as 56.71 mm. 56.71 mm. Now we need to see the condition for the maximum spacing. You can see clause number 41.4.3. But the total transverse reinforcement shall not be less than tau VE minus tau C into B SV divided by 0.87 Fy. From here you will get the maximum spacing as 0.87 Fy divided by SVE minus tau CB into ASV. You will get that value, and you will get that value as the maximum spacing criteria based on the shear reinforcement. Also, you will get based on the other two criteria, you will get the maximum spacing as in clause number 26.5.1.7, you'll get when a member is subjected to torsion, the torsional reinforcement shall be provided as follows. The transverse reinforcement for torsion shall be rectangular closed stirrups placed perpendicular to the axis of the member. The spacing of the stirrups shall not exceed the least of x1 or x1 plus y1 by 4 and 300 mm, where x1 and y1 are respectively the short and long dimension of the stirrup. So there are three conditions for your maximum spacing. There are exactly four conditions based on the minimum area of shear reinforcement, then by x1 plus y1 by 4 and 300 mm. Now I will explain you what is this x1 and y1 in detail. That is from clause number 41.4.3, you have the maximum shear reinforcement. ASV must be greater than or equal to tau VE minus tau C into BSV divided by 0.87 FY. This is clause number 41.4.3. From here you will get SV must be less than or equal to 0.87 FY ASV divided by tau VE minus tau C. Here the only change is on the last one is we have tau VE instead of tau V. So here you will get SVS. Substituting these values, you will get SVS. SV, that is the minimum. So the maximum spacing is 0.87 into 415 into 2 into pi by 4 into, now we have assumed 12 mm stirrup, that is 12 square divided by 3.26 minus 0.61 into 600. There is B, sorry, into 600, that is we will get this value as 51.36 mm. That is we can provide a maximum of 51.36 only. Now from clause number 26.5.1.7, page 48, you have the values for the minimum shear maximum spacing as x1 or x1 plus y1 by 4 or 300 mm. Now x1 is the distance between the stirrups in the horizontal direction or along the width. That is, I could take it as the distance between center of this to center of this. So this is 12 mm, 2 legged 12 mm 5. So center to this is x1, and y1 is from here to here. This is y1. Center of this to center of this, we will get the value for y1. So x1 I could write it as, so x1 means the distance from here to here. So this distance is actually b1. This distance is b1 plus half the diameter from here and half the diameter from here and half the stirrups diameter from here and half the stirrup diameter from here will give you the value for x1. That is, I could write x1 is equal to you can write here, that is b1 value, that is 500 plus this is 28 mm diameter bar, that is 14, and here it is 28 mm diameter bar, that is 14. That is b1 plus 14 plus 14 plus this is 12 mm diameter stirrup, that is 6 plus 6. That is, I will get this value as 500 plus 14 plus 14 plus 6 plus 6, that is 540 mm. Similarly, y1 I will get it as, that is the distance from here to here, that is d1 plus here this is 28 mm diameter bar, 14 plus 6, and here it is 16 mm diameter bar, that is 8 plus 6. That is d1 y1 I'll get it as 700 plus 14 plus 6 plus 8 plus 6, that is 734 mm. Now if we see the maximum spacing criteria, I have x1, either x1 maximum spacing, that is from clause number 6.5.1.7, page number 48, I'll get maximum spacing as x1. x1 is 540 mm or x1 plus y1 divided by 4, that is 540 plus 734 divided by 4, you'll get that value as 318.5 or 300 mm, whichever is lesser. So we have the maximum spacing as these three value, and from this we got the maximum spacing as 51.36. We cannot provide a spacing more than this 51.36 based on this maximum reinforcement criteria. So we will provide 12 mm 5 at 50 centimeters and 50 mm center to center. Now the transverse reinforcement design is done. Now the remaining is the side face reinforcement. So if you take clause number 26.5.1.7b, the longitudinal reinforcement shall be placed as close as in practicable to the corners of the cross section, and in all cases there shall be at least one longitudinal bar in each corner of the ties that we have provided. When the cross sectional dimension of the member exceeds 450 mm, additional longitudinal bars shall be provided to satisfy the requirement of minimum reinforcement and spacing given in 26.5.1.3. That is, when it is subjected to torsion, we need to provide additional longitudinal reinforcement as side face reinforcement when the depth is greater than 450 mm. So that is 26.5.1.3. If I go to the 26.5.1.3, that is a side face reinforcement when the depth of the web in a beam, that is a normal beam where there is only flexure and shear, is greater than 750 mm, side face reinforcement shall be provided. But when it is subjected to torsion, we need to provide when the depth is greater than 450 mm. The total area of such reinforcement shall be not less than 0.1% of the web area and shall be distributed equally on two faces at a spacing not exceeding 300 mm or web thickness, whichever is less. So now we will provide the longitudinal reinforcement. It is clause 26.5.1.7b longitudinal reinforcement. In that, if you read, you can see we need to provide side face reinforcement when depth is greater than 450 mm and it is accommodated by torsion. You can see in clause number 26.1.5.1.3, that is, we will provide, I will denote the side face reinforcement as A suffix SSF is equal to 0.1 by 100 into web area, that is B into capital D, that is, I will get this value as 0.1 by 100 into 600 into 800. This value I will get it as 480 mm square. So if I am providing 12 mm bars, then I need to provide, this is the minimum area of side face reinforcement, that is 1% of web area. So if I am providing 12 mm bars, then provide 12 mm bars, then number of bars is equal to 480 by pi by 4 into 12 square. I'll get this as 4.24 numbers. I'll round it to 6 numbers. That is, we need to distribute it equally along the side of the bars. Now provide 3 numbers 12 mm on either side with a spacing of, then the spacing should not be greater than 300 mm or 600 mm, that is the width of the beam, whichever is lesser. So provide 3 numbers 12 mm 5 H 250 mm center to center along the side of the stirrups. So S side face reinforcement. So when I am coming here, that is, we need to provide 3 12 mm bars. I will provide it here. We need to provide 3 12 mm bars, that is 1 2 3. 3 12 mm bars will be provided at a spacing of, the spacing, you see what is the spacing, 250 mm. So we have taken the largest as 300, so we will provide it as 250 mm center to center. So this is the complete design for torsion of a rectangular beam section. Hope you have understood this. And from next class onwards, we will start with design of slab. That is your next module. So I hope you are clear with this. If you have any doubt, we can discuss in the live session. Thank you and have a nice day.